Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started today, I have just a couple administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we do not address your question, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's webinar will focus on effective design and implementation of vapor intrusion mitigation systems for new construction. With that, I'd like to introduce our presenters for today. We are pleased to have with us Tom Hatton, CEO of Clean Vapor LLC. Tom is a highly sought after speaker, consultant, and vapor mitigation system designer with over 30 years of knowledge and expertise. He is an industry-leading expert in delineating how environmental conditions and building dynamics lead to vapor intrusion. As a co-author and contributor to many state and national mitigation standards and guidance documents, Tom leads LSRPs, PEs, and building owners through the increasingly complex regulatory landscape on vapor intrusion projects. We're also pleased to have with us today Jordan Knight, National Sales Manager for Land Science, a division of Regenesis that provides industry-leading vapor intrusion barrier technologies for contaminated sites. Jordan Knight has extensive experience in managing brownfield and landfill redevelopment projects where vapor intrusion barriers and venting systems are implemented throughout the United States. She also serves as co-chair of the membership committee for the Association of Vapor Intrusion Professionals. All right, that concludes our introduction. So now I will hand things over to Tom Hatton to get us started.
Well, thank you very much. I appreciate that. I appreciate the opportunity to be here and share with Land Science some of the things we've been doing. So today's topic is protecting people from the sixth side of the building. Now we know that when buildings are constructed, a lot of time and money is put into picking the location, the appearance of the building, the design, the marketing, and everything else, but not so much into what actually protects the people from what's below that building in the ground. And what we're going to do today is we're going to discuss that, and hopefully by the end of this, you'll have a much broader understanding of how to protect people from the sixth side of the building. So our mission at Clean Vapor is to make indoor air healthier for people who are living and working in buildings that are affected by vapor intrusion while reducing long-term liability for developers, building owners, and responsible parties. It's always been our guiding principle that if we put the structure of the building out in front and the people out in front and do our best in terms of thought and design, that we can come up with a product that will be protective of people and owners at the same time. So what is vapor intrusion? Well, vapor intrusion is the upward migration of soil gases into buildings. Typically, the things that we deal with are volatile organic compounds, TCE, PCE, carbon tet. We also deal with fuels on the petroleum vapor intrusion side, which are gasoline, diesel, and other types of products. Other possible contaminants are mercury, hydrogen sulfide, methane we're going to talk about a little bit, which is a naturally occurring contaminant, as is radon. But typically what we deal with are the VOCs and the petroleum hydrocarbons. Normally what happens is there's industrial sites, gas stations, dry cleaning facilities that use these chemicals, and they get spilled or discharged into the ground. It seeps down through the soil, floats along on the groundwater until a low pressure is encountered, and then those contaminants are drawn back up into buildings. Or sometimes there's a former building that's been raised and there's contaminants that are in the ground or on the groundwater that are going to affect a new building. So we want to be able to jump out in front of this and provide a protective system that will protect the occupants of these buildings. So let's talk about what are some of these contaminants. There's the naturally occurring ones and there's the man-made contaminants. We have our petroleum hydrocarbons, which we talked about. There's a lot of corner gas stations out there, thousands of them across the United States that have leaked. There's also chlorinated solvents and other types of compounds that are in the soils. Now, as our population is growing, what was once kind of industrial property or gas station property is now high value downtown real estate property. So we have to look at protecting people who are in these buildings. One of the unspoken things that's part of this business is naturally occurring radon. Radon is in all soils, and radon, according to the US EPA, is the most deadly thing that it regulates. The compounds that we're talking about, your VOCs, your petroleum hydrocarbons, are regulated to a cancer risk of 10 to the minus 5 or 6, which means a risk of 1 in 100,000 or 1 in a million. But naturally occurring radon is only regulated to a risk of 7 persons getting lung cancer out of 1,000 at 4 picocuries. So there's a 3 order of magnitude difference between what we're going after with petroleum hydrocarbons and VOCs compared to naturally occurring radon. And if you're building a building, you have to be protective from all contaminants, not just the ones that showed up in a TO15 test or an environmental study. And there's a huge gap in education in this country as to what these contaminants are and what their impacts are. This slide right here is an excerpt from an actual email from a project that we were involved with. And what it says is Steve wants to avoid radon system if possible, $, $. Now that tells me a couple things. Possibly Steve does not understand the risks associated with radon. Possibly Steve doesn't understand the long-term liability for the building owner. Or possibly Steve just knows those things, but is being pressured to deliver a profitable project for his construction group and is choosing to bypass these things. Anyway, radon cannot be ignored. It's responsible for 21,000 deaths annually in the United States. And as we build more new properties, this problem is not solving itself, it's actually getting worse. So you want to think about the total sum of contaminants inside of buildings. Furthermore, there's other contaminants. There's mold from organic decaying material that can get drawn up into buildings. There's methane, which there's 2 different types of methane. There's thermogenic methane, which comes from your deeper sea decay. It's mostly your oil deposits like the LA basin is historical methane, but mostly what we deal with in our industry is biogenic methane. And that's the decay of organic materials that are near surface. And it could be like in Florida, where you have anywhere from a few inches to a few feet of decaying material from cabbage palms, or mostly what we deal with is buried wood and garbage. There's also issues of mercury and hydrogen sulfide, and that gets a little bit more complex. The hydrogen sulfide is pretty easy, but the mercury, depending on the oxidation level and the size of the beads in the soil and so on, can be more complex. But these are all things that we need to think about that are in the soil and then protect the people who are in those buildings by designing an effective vapor intrusion mitigation system. So we have all these soil contaminants in the ground. And what's the problem with that? If they stay in the ground, they're not a problem, right? Well, the reality is that buildings are temperature regulated. Most of the time, they're around 70 degrees. And what happens is, just like the warm air in a hot air balloon pulls that basket up as it rises, the difference between temperature inside a building and outside a building is the largest driver of vapor intrusion. The second largest driver is the wind. But in a hot air balloon, the wind comes along and it just pushes the hot air balloon along in the wind stream. But on these buildings, what we have is eddy currents that occur on the backside of the building and exacerbate that convective flow of soil gas into the buildings. So we really have to build something that's thought out really well on the bottom side of the building to protect those people who are going to be on the inside. So this is where it starts getting a little bit complicated. There's a lot of standards documents out there that say different things, but you want to go, if you're designing something in a particular state, you want to go to that state and find out what is the correct standards document, because this determines what your end goal is, and it will also determine what you're legally responsible for. So that's where you want to start out. What am I doing? Where am I going? And not every state has specific guidelines for construction. A lot of that's really open to the designer. Our ANSI has put together some standards which are kind of like a great cookbook for radon. They have some applicability for VOCs, some general guidelines, and really nothing about methane. So you have to figure out there is some referenceable standard that you're going to work with, and then usually have a conversation with your regulator and saying, I am designing to this, or put a footnote down, designed according to this standard. There are 16 states out there that don't have any regulation at all. And so if you're working in any one of these states, what you want to do is look at the EPA's VISL, which is the vapor intrusion calculator, and find a standard for those contaminants, and then reference your rationale as to why you did that. You don't want to overprescribe either, because that can become a problem where they come back later and say, well, we didn't really need this and you're responsible for all these extra costs. So you want to have documentation for every decision that you make. Also, you want to make sure that you are working with the absolute most current version of guidance document. California released their final draft just last month. So you want to make sure that you reference where that came from. We're involved with consulting on a legal matter where a consultant designed something to 2017 standards, which is the most recent document for that state. And then the consultant that they hired to critique the system did the critique based on 2008 standards, which created a bunch of unhappy people. So make sure that you have the most recent document so you can set the end goal of what the performance for your system is going to be. And achieving the specifications in terms of indoor air quality and pressure differential that's specified in these documents is absolutely critical. So let's back it up a little bit, and we're going to talk about the CSM, which is the conceptual site model. And this is the part where if you're a vapor intrusion mitigation designer or installer, you kind of defer back to the environmental consultant. And what they're going to do is they're going to take, the 10,000 elevation look at this site and said, what are the contaminants in the ground? Where are they on the groundwater? Where is there a plume that's moving in a particular direction? And what type of protection do we need to prescribe or recommend for this particular building to make sure that occupants aren't impacted? What are the particular chemicals that are in the ground? Different chemicals have different thresholds for toxicity and concentrations that are permitted below buildings. There may be things that you may think are really bad and possibly they're not, or there may be things that you're very used to, like PCE from dry cleaning fluid, because you pick up your suit or clothing all the time, you smell it a little bit, you think it's really not that bad, maybe it's not a big a problem in the ground, but maybe in reality it is. So you want to find out what you're dealing with in that you're protecting the interior of that building from those ground chemicals. So new construction. There are guidelines in most regulatory documents. This one here is an excerpt from Tennessee, where it has the risk factor, and you can get these numbers out of the VISL, where it says in Tennessee that 10 to the minus 6, or cancer risk of 1 in a million, mitigation's not required. But if you go over 10 to the minus 5, which is 1 in 100,000, then mitigation is required, passive or active. So if you're designing a system, you always want to make that passive system a passive system that can go active. And that means putting the pressure differential probes in the ground, the sampling ports, specifying the motors, running the conduit from the power supply on the first floor up to the roof, just below the roof, so that blower can be powered. You don't have to put wire, leave a string in it, but just have it ready to go. And then if mitigation is required, and this is kind of the guideline, and this is your rationale, and if you have a reason for not mitigating, it's here in this table. But Tennessee and North Carolina are joined states. Flip over to North Carolina, one county away, mitigation would be required at 10 to the minus 6, which is why you want to make sure that you understand the rules of the road before you get going with your project. Also, in the conceptual site model end, ITRC has some really good guidance. There's a flow chart. You can go look that up and kind of think your way through it and work with the environmental consultant to come up with a rationale of what you're doing, why you're doing. My personal opinion is, and this has been the philosophy of Clean Vapor, we have always pushed to make passive mitigation work for our clients. And there's a reason for this. It's a clean slate. We can hide all the pipes. It's far less expensive than doing anything afterwards. But if you can get something to work passively, and that means without a motor, there's minimal long-term carry costs on that building. You're not trapped into endless monitoring or endless sampling. And also, if you can get that NFA because you designed that underslab system so well that it worked like a charm just on barometric pumping or convection through the wind, how it goes over the pipes above the roof, this is an absolute home run, and it is the best cost savings device long-term for the investors on that building. So once you gather all this information, what you're going to want to do is pull all the stakeholders together. And what that means is the environmental consultants, the developer, the regulator, the VIMS, designer, installer, and the attorneys. And you get everybody on the same page. This is really critical. And this is where I've seen a lot of projects go wrong when this gets overstepped or not taken seriously, because you get halfway through a project and all of a sudden there's a problem. And we go back, you said this, we didn't agree to that. And the thing is, when you bring the attorney in, they take lots of notes and then they send out notes usually after the meeting. It's because they're going to want to be protective of the client and quite honestly themselves. That is a good guide for this type of project. That way there's a constant check. And if there's something that doesn't comport legally, they can put their hand up and say, hey, I think you should do this. Or if there's an issue with the regulator, they're going to be the ones sending the letter. So there's a very clean line of communication. So once you're past that, you're kind of thinking into the design phase. How is this building going to be built? You want to talk to the construction guys. What is the sequence of this building? And that's where you're going to pull the architect probably in and say, what is the construction sequence? How is this going to be built? Because you want to integrate the installation of the sub-slab plenum piping and vapor barrier and whatever else you're doing to get done as fast as possible. Now, with today's interest rates, this is even more critical than it was just a few years ago, because these investors are putting up money and they don't see a penny back until this space is occupied. And the last thing you want to do is be the vapor contractor that held up the production of a building. So, design essentials. These are the broad-based things that you need to know before you get started. You want to understand what the contaminants of concern are. We've talked about that. You want a clear definition of the building area that needs to be serviced. Now, sometimes you may be a building that has several different slabs and different elevations, and maybe only one corner of that building is going to be impacted. So maybe you don't have to have such a robust system across the entire building, but there has to be a reason for that. It has to be documented. You want to get a complete set of structural drawings, which is going to have all the elevations, pile caps, everything else that goes along with this. And you need to understand the building's use. Different buildings have different use groups, which require different materials, such as sometimes pipe will have to be metal. If there's so many stories, it may need to be metal pipe. There's a bunch of different things that are determined by the use group of a building. Understand all the elevations, the finished floors, where the HVAC intakes are, and you want to look at what are some potential project snags. Elevator pits are a huge issue. They have to be done separately, usually out front. Is there subgrade drainage? A lot of times an architect, even though it needs a vapor intrusion mitigation system, may and design a sub-slab drainage system that goes to daylight, which is going to totally short circuit your vapor system. Another thing that we see quite commonly with architects is they will give the vapor intrusion mitigation system design to the newest architect, somebody who's not familiar with vapor intrusion. And what we see multiple times is we'll get a plan design and it will have some type of loop pipe that will run over 3 levels of elevations, including ramps and all kinds of things, not showing how to do this. So if you're going to have the same pipe on 2 different elevations, that needs to get planned in at this stage. And that's where you're talking pretty tight with the architect to get all that worked out. Elevations are critical. Site elevation is really determined by what the elevation of the existing ground is, the elevation, the thickness of your stone plenum, your vapor barrier, and your DGA level. Now, I'm showing you a slide here on the lower part of the screen. This is a large airport basin in New Jersey where we did well over 1 million square feet of designs for several different buildings. And the goal of this particular developer was to have everything passive. And this was really tricky because this site historically was manufacturing buildings and a lot of things that have to do with fuels from the airport. So there was high groundwater, silty soils, and a cocktail of chlorinated solvents and fuels. And the goal was to go passive. And these soil gas concentrations in the predecessor buildings were in the neighborhood of 1 million micrograms. But what we did is we were able to figure out the correct stone bed height, the pipe diameters, the conveyance, get everything worked out, and work with the elevation. So if we have between 8 to 11 inches of stone and 3 to 4 inches of DGA, and you're talking about a 400,000 square foot big box building, that's a critical elevation, or even a 200,000 square foot building, because we couldn't take any soil off site. So if you start building up the elevation of the inside area, then all of a sudden out in the parking lot, you have a problem with drainage, runaway shopping carts, and all these things because of slopes. And all this needs to be figured out and conveyed and the site adjusted. This all happens at the front end with the architect. You also want to think about what is the sub-slab conveyance material. If you have something like 57 stone and you want to have an active system, you can put vacuum on it and it may go 65, 70 feet. If you have Piedmont clay, there's not a chance in the world you're going to depressurize that. You need to put down a good stone conveyance layer and then have pipe and stone. And there's formulas for this that build in efficiency, and we spent years figuring them out. We've kind of optimized that. It's one of the niches of clean vapor. You want to get all these design elements, this conveyance system. You don't want to have anything isolated below a slab. Now, if we go back to the RST documents, it's 64 square feet. And the origin of this is based on the coat closet size inside of schools. So when public schools are being built, and a lot of times there's haunches or thickened slabs that have to do with closets, and they decided, well, okay, well, that will be the smallest amount. But that means every bit of what's underneath the slab of that building needs to be connected to one of these pipe conveyance systems. And there's different ways of doing it with flat pipe. There's a jumper in the center slide and these plenum boxes, which work out absolutely phenomenal for grabbing large areas on a 6-inch pipe and putting that up through a riser. Other design elements are your risers and your venting. You want to make sure that you have sufficient area on each pipe. And there's some rules of thumb on this. Like you don't want to have more than 1,500 square feet on a 3-inch pipe. There's usually around 4,000 square feet for a 4-inch pipe and another area for a 6-inch pipe. You want to use materials that meet the building codes. You can see this here is a public school building, and it's metal pipe because it needs to be protected as dictated by the use group. You want to make sure that that venting is at least 20 feet away from intakes that are powered. Also, passive relief vents. I can't tell you how many buildings I've been out to, and they forget about the whole vapor system right to the very end. Then somebody runs it up the sidewall of the elevator shaft. But what happens when the elevator goes up and down? It's like a giant plunger, and it just sucks that air back in through the passive relief vent there. So you want to make sure that you're sufficient distance from anything that could re-entrain soil gas into the building. Now, what these states required is performance verification that what got designed is actually functioning. And there's two ways that that gets done. One is by measuring pressure differential. Now, different states have different rules for pressure differential. Many states are 1 Pascal, which is 0.004 inches of water column pressure differential at the outer extent of the negative pressure field during adverse conditions. Other states tie in both subslab and indoor air. Now we go back to that airport basin that I talked about. The reason there is no motors on any of those systems is because we designed it in a manner where it would efficiently vent to be below the state's threshold of subslab soil gas for activation. And then that's a good goal. But part of the problem is there's a matrix as to where all these ports have to go, and that's determined by the regulators. But you can't get back to them. After a building is built, particularly a multifamily building, you're not going to get back in these buildings. There's Rottweilers, piles of rancid laundry, people doing drugs sometimes, and you just can't get back in there. The same thing with big box stores. You may have a pressure port, and guess what? There's a giant end cap rack of soup cans there. You're not getting into it. The purpose for putting these ports in is that you can have a continuous line of data to demonstrate proficiency. So the best way to do that is have these things embedded, and you bring them up to centralized panels where you can have telemetry like we have here in the slide, or at least get to there and do your subslab samples. Now, the cool thing about this, if you're doing a big box, you may have 28 or 30 some sampling ports below the slab, right? You bring them all up in your panels, you can get your pressure probe readings and your samples done for the entire place in a couple of hours. And for states that require multiple rounds, this is the absolute way to go. Next step, talk about vapor barriers. Now, there's a difference between vapor retarders and gas barriers. Typically, your vapor retarders, and this kind of came from the evolution of building when they realized that they needed some way of separating moisture in concrete. Polyethylene is not a gas barrier. It is a retarder. It is a water permeance barrier only. And the American Concrete Institute, ACI, has set up standards for permeance to evaluate these vapor retarders. So if you see chemicals of any type or anything that even by pH could degrade polyethylene, you want to shift immediately into a more protective vapor barrier. And there's very limited application, in my opinion, for this polyethylene except for water permeance. And this is where land science comes in, because they've spent a lot of time developing barriers that are going to be protective from those chemical elements that are the most harmful for people. Having a gas type barrier that's chemically impervious is, in my opinion, absolutely essential. We're going to show you not only the health protections, but the cost savings at the end of doing this right. You want to have a spray applied vapor barrier that gets those seams gas tight. And I don't care what anybody says, you cannot get tape to stick to column pads, sidewalls, as well as you can a spray applied barrier, because this spray applied material, when you spray it down, it's tacky, it's like an adhesive. And what it does is it fills up all the pores and bubbles in the concrete, and you can get a nice gas tight seal to that particular column right there. So let's talk about vapor barrier lithology a little bit. You're going to start with your subgrade, your proof rolled ground. The next thing you're going to do is you're going to put down a geotextile fabric layer. What that's going to do is that's going to keep the soil particles from getting in your crushed stone and including that crushed stone. Now, if you have a high water table, that is absolutely going to happen. Then you're going to put down your crushed stone layer, and that's where you're going to put your vapor collection piping. You're going to put your pressure probes that are going to go to that centralized panel. The next layer that comes down on top of that is sometimes on certain sites you have to work with flat pipe, which is your Terra vent. That can go over the top of the stone layer and be in the top layer, because a lot of times in that stone layer, there's drain pipes, there's all sorts of things that would cut off the extension of vacuum or prevent the conveyance of air into that upward truck line. The next layer that comes in is your geotextile fabric, and then your spray applied can go on top of that. Then there's a protective layer of fabric. And here's where it gets a little tricky, because you want to have a DGA layer, that's dense graded aggregate. That's where you can run your electrical conduits and other things. It also allows you to make repairs much easier. Now, there are some states out there that want to have both pressure differential readings from below and above the barrier, as well as chemical samples from above and below that barrier. And we try to make the point that the slab is part of the barrier system, and then they come back and say, no, it's actually the vapor barrier. So there's this trend that's happening where they want pressure ports both in the gravel layer and the DGA layer to demonstrate the effectiveness of the vapor barrier. But doing this correctly takes a lot of thinking out front. It takes agreement with the architect. But if you do it correctly, this will create an absolute protection layer that can be documented and verified through performance testing of what gets collected through these probe systems. And in my opinion, every building's a little bit different, but there is an optimum solution that involves some subset of all of these layers. The next thing you want to do is gas test these barriers. And this can be done with smoke testing. And this is what differentiates a gas type barrier usually from a tape system. Very rarely are you going to see in the specification of a tape system anybody daring to recommend smoke testing. And this is kind of what the smoke testing looks like. You pump it below the slab. Any leaks and openings in this barrier will automatically come up. You can identify them and you can go and seal them. And this was kind of cut open for the demonstration of this video, but this is the absolute way to go. And then somebody signs off on it that this column area of the building by that column area of the building has passed a smoke test on this day. And that will give you the record that you need. You hold on to that because that goes into your commissioning documents at the end. So this is what a smoke test looks like. Other things you want to do is you want to think about installation considerations, managing the site. You want to talk to the GC ahead of time. You want to figure out how the site is being sequenced, where you can store things, time of delivery, getting back to speed of construction. If it's going to be cold, you're going to want to have some place where you can put spray applied material to keep it above 40 degrees. Also, it doesn't hurt to keep this stuff boxed up because you don't know how secure the site is. But all these things, you want to have these conversations up front. So when you get on site, you are snapping along and you're not holding that GC up one bit. Now, once it's all done, the slab is poured, you're going to want to performance test this. You're going to want to have a record of what you designed actually functions. And there's some kits out there made by companies from Fantech, or you can do it yourself. You place a blower on the pipe, you measure the vacuum that's applied, you measure the outflow of air, and you measure the pressure differential. Now, this is where a spray applied vapor barrier or a true gas barrier will distinguish itself from polyethylene. We did a building, it was 22,000 square feet. We applied 2.7 inches of vacuum on a fan like this, and every pressure probe below the slab measured between 1.79 and 1.83 inches of vacuum, which means that we extended 1.75 inches of vacuum underneath the entire slab, just with the standard fan at 90 watts, and we only exhausted 119 CFM, which means a little tiny blower can do that entire building if it does need to go active. Now, on the chemical side, there's also performance verifications. Now, typically what happens is the regulators may want you to do sub-slab samples. Those are things that you can get through that network of tubes from a single panel. And there's matrices that are set out that set for the frequency of those samples. Typically, every isolated slab up to 1,500 feet is going to need one sample. Sometimes some states will require two. Now, there's also indoor air sampling that goes along with this because they want to have demonstration that what was designed and installed actually works. And there's a frequency for that. So usually what happens is the first year, they're going to want quarterly sampling, or some states are heating season, which is winter and summer, but there is some type of requirement for indoor air sampling verification. Now, the reality is, if you have an active system or you have a passive system that at least maintains 1 Pascal, 0.004 inches of water column at the outer extent of the negative pressure field, you are not going to have a vapor intrusion problem. We've been designing these systems since 1988, and we've not had to put a motor on one system yet. And that's because we focused on efficiency, but the state guidelines are the state guidelines, so it's all followed up with the contaminant sampling documentation. A lot of times what we'll do is we'll put telemetry on this. There's some states that want to see pressure probe data, being the pressure differential data, monthly. It just doesn't make sense to go to a building where there's just maybe 30 to 50 probes below the slab and get data from everyone every month. It's not going to happen. So you put it on telemetry. And the cool thing about telemetry, there's an hour by hour documentation of how it functioned. Your more thoughtful developers are going to go, this makes a lot of sense. Their attorneys are going to say, this protects you from liability. It's just the way to go. And particularly if there is a possibility of a tort action. All it takes is a person with cancer to come in and start a tort action. If you don't have documentation, it could be a problem. Also, one of the things you need to do is have some type of best practices manual. How do you maintain this? Kind of like when you buy your car, you get a maintenance manual. Well, this is where the DGA layer and things like that really come in and become beneficial. If you're doing a strip mall that's going to be cut up with pipe pathways and everything else, and you're going to be putting in chicken fryer degreasers, this is going to get cut up a lot. And this is where you want to put the DGA layer in, because you just set your saw blade to the depth of the concrete, you cut out your slots, you peel back the barrier, put in your piping, put it back together, spray a patch on it, close it all back up, and you've documented that it's done correctly. It's kind of hard to do when you don't have this DGA layer in there and the concrete is stuck to the top fabric or the spray applied layer itself. You want to have a commissioning document at the end that says, this is what we installed, this is how we did it, this is how it performs, this is where all the pipes are, this is what we have in terms of our pressure differentials and our sampling documentation. Typically, this package will go to the regulator, but you will maintain it, the attorney will retain it, and there will be a record of what went on in this building. You'll have proof of performance and protection. We just went to activate a building up in the Midwest. It had a system on it. We put a fan on it. The fan was maxed out, no airflow. We can't measure vacuum 14 feet from the suction point. There's a problem. We don't know where any of the pipes are. Don't get caught in that trick bag. It's something you want to do correctly. Again, right now we're at the end, and we're going to look at the energy efficiency and the cost analytics of tape seams versus sprayed applied barriers. This is based on some buildings that we've installed where we've been the installation contractor on polyethylene versus spray applied vapor barriers. So this is based on an active system and the leakage when vacuum is applied. There's a lot of leakage associated with these tape systems, which means that conditioned air from the building is being pulled down backwards through electrical conduits and all types of other openings into the subgrade. So you're pulling heat out or conditioned air out, exhausting it up. Also, you're not going to get the vacuum field extension because of the leakage. So you're going to have a motor that's running, and then you're going to be losing heat. So what we did is we did a study and we normalized these prices. And what we found out was that if you equilibrate this to 10,000 square feet of building, these type of savings combined can be up to $1,000 a year per 10,000 square feet. So if you have a 50,000 square foot building, you can be saving $5,000 a year just in energy costs from installing an efficient system. So what this looks like is maybe there's some more money on the front end to do it right, but you hit year 9.5 through 13 someplace. Those savings are all going to come back to you, and you're going to be in positive cash for the entire lifespan of the building. Not only are you going to have better protection, but you're going to get better ROI on your money, which is really important if you're in the investor component of this. So I want to thank you for the time today. If we can support you in any way through Land Science, we're happy to do that. My name's Tom Hatton. I'm also president of the Association of Vapor Intrusion Professionals and CEO of Clean Vapor. And you can find me through the email or Land Science. And right now, I'm grateful to hand this presentation off to Jordan Knight.
Good afternoon, everyone. I appreciate those of you listening in today. For those of you joining us for the first time, I'd love to just kind of reintroduce myself. I'm Jordan Knight. I'm based in Chicago, and in my current role here at Land Science, I operate as our national manager. I am responsible for leading the land science territory managers that are positioned across North America. I have been with Land Science for nearly 10 years now, and I truly love supporting developers and consultants in brownfield redevelopment opportunities. I do want to take a quick moment and just say thank you to Tom Hatton and his team at Clean Vapor. It's been very enjoyable of a process just working with him and developing this presentation and him sharing his expertise with us today. So I am looking forward to building on some of the points that he brought up related to best practices for vapor intrusion mitigation design development. As we just heard, Tom highlighted the importance of incorporating contaminant vapor barriers into his overall design process. And today I'm going to share with you just several advanced vapor barrier technologies that can be implemented into a site's VI mitigation plan. And that is going to help minimize the risks that often come with contaminated site redevelopment. So for those of you that may not be familiar with Land Science, we are a division of the global remediation company Regenesis. Our mission here at Regenesis and Land Science is ultimately to simplify the environmental remediation and vapor intrusion mitigation process by manufacturing cutting-edge, cost-efficient technology solutions and providing exemplary technical service and support. So for the last 15 years, Land Science has been an industry-leading manufacturer of advanced vapor intrusion mitigation technologies. What's unique about our story at Land Science is that our parent company, Regenesis, is approaching 30 years of success in pioneering, commercializing, and manufacturing advanced in situ technologies for soil and groundwater remediation. They have experience with remediating over 30,000 sites across the globe. So when you're working with our team at Land Science, you are partnering with a team that is intimately familiar with contaminated site redevelopment. We have been involved in nearly 100 million square feet of buildings to date with our vapor intrusion barrier and subslab venting technologies. So Land Science, we offer a full suite of contaminant vapor barrier systems, and they offer superior chemical vapor resistance properties as well as ease of application, making them an ideal technology for protecting building occupants and mitigating risk. So when working with our team, you can expect a tailored solution that meets your project goals because we offer a variety of vapor barrier technologies, and each of those are designed for a wide range of site conditions and are backed by our industry-leading warranties. Peace of mind is built into every Land Science installation with the most experienced network of certified applicators, as well as the industry-leading certified inspector training program for environmental professionals. Built on a foundation of technology innovation, Land Science invested nearly 5 years in research and development to advance the historic spray applied barrier system technologies that were available to design engineers. And as of 2019, we delivered 2 major vapor barrier material advancements to the environmental and construction community. And that is through our metallized film geomembranes, as well as our nitrile modified asphalt. These material innovations ultimately increase the chemical vapor resistance properties of our barrier systems. So as Tom mentioned, long-term protection against contaminant vapors is truly what the industry expects and what evolving regulatory standards require. And we found that by incorporating metallized film within our barrier sheet materials, it provided orders of magnitude greater resistivity to contaminant vapor diffusion through that material. So as you can see here from this normalized comparative analysis, our metallized film base layer, TerraBase Plus, versus a 10 mil HDPE base sheet that's commonly used in traditional composite barriers. You can see the reinforced metallized film layer was over 140 times more effective at preventing TCE vapors from fluxing across that material when subject to identical testing conditions. So ultimately, the base layer with the metallized film was 2 orders of magnitude more resistive to TCE than the polyethylene-based layer. So the other significant advancement I referenced is our nitrile modified asphalt. Traditional spray applied vapor barriers, even including our own legacy technologies, those were born from the waterproofing industry and have often been considered good enough for vapor intrusion mitigation. But really, there's no longer a need to settle for just good enough. Land Science now manufactures a proprietary nitrile modified asphalt that is formulated specifically for contaminant vapor mitigation. So by adding nitrile into our spray applied formulation, we saw up to an order of magnitude greater resistivity to TCE vapor flux versus the older generic spray applied technologies that we had offered. And that was represented by the red line in this graph. So from a mitigation system design standpoint, this translates into a much more reliable long-term mitigation strategy, particularly at vapor barrier system weak points. Tom had alluded to, at seams, utility penetrations, building perimeters. Those locations now offer up to 10 times more resistivity to vapor intrusion with a nitrile modified asphalt. So from those 2 material innovations, the metallized film geomembranes and the nitrile modified asphalt, we improved upon our older technologies to now offer 3 spray applied vapor barrier technologies for the environmental and construction industry. And that's through our TerraShield, NitroSeal, and MonoShield systems for new construction. And these have been rapidly adopted by the industry for contaminant vapor mitigation. I do want to note, we also do offer a vapor intrusion coating system. This is designed specifically for existing building mitigation, and that technology is known as RetroCoat, which has celebrated over 10 years of performance in VI mitigation and is an excellent option to consider either in conjunction with or in lieu of subslab depressurization systems. So here's a look at our TerraShield vapor barrier system. This is a patented 3-layer composite membrane, which consists of our 25 mil reinforced metallized film base layer, the TerraBase Plus. It includes a 40 mil spray applied application of our NitroCore, which is the nitrile modified asphalt. And then it's topped with the Land Science protection fabric, and that's designed to withstand ultimately the next phases of construction, whether that's rebar placement or the concrete pour. TerraShield offers the highest level of protection in the industry, and this has been installed and really is intended for moderate to high risk vapor intrusion sites requiring maximum protection from VI or liability exposure. We often see this technology specified for either institutional or residential applications, whether that be daycares, senior living communities, residential developments, hospitals, schools. This particular site you see here is a residential site that we're working on right now, where you can see the TerraBase Plus layer being rolled out, the seams being sealed, and you can see the 40 mil application of NitroCore across really the majority of the building footprint. NitroSeal is another composite membrane system, and this creates a redundant, protective, and cost-efficient gas vapor barrier system. The components of this barrier include the 22 mil NitroBase Plus layer, and that is a polyethylene sheet thermally bonded to a geotextile on the underside. And this is followed by a 40 mil application of the NitroCore, and then topped with an 18 mil land science bond layer. And that includes HDPE as well as a geotextile bonded to that sheet material. This drone image shows an installation of a NitroSeal application on a project site where we worked with Tom's team at Clean Vapor to help support mitigation of a public library complex. So this technology, it's really is ideal for moderate risk VI sites, and it's a popular solution for residential developments desiring a long-term solution. The spray applied nature of our systems and our certified applicator network really make for an efficient application out in the field. And each of our vapor barrier technologies offer a high level of constructability. And that's really a crucial component of any vapor barrier evaluation process. The reinforced grid and the underside geotextiles within our sheet layers, those are designed for optimal durability across a range of substrates and foundation types. And then the multi-layer composite systems offer really the redundancy necessary to withstand the rigors of construction sites. So the last system I'll share with you guys today is our MonoShield system. This is a patented single layer 30 mil geomembrane, and this consists of metallized film, and it's reinforced with a polyester ripstop grid that is encapsulated by layers of polyethylene and has a thermally bonded geotextile fabric on the underside of the barrier. So this is a very robust, rugged membrane system. The MonoShield system was designed specifically for implementation across slab-on-grade industrial warehouse developments, as you see here. You can see the mono base sheet good and the NitroCore being used to seal off the seams. It's also used for addressing penetrations and termination points around the building perimeter. The mono base layer, it provides excellent tear and puncture resistance due to that polyester reinforced grid as well as the underside geotextile. And the metallized film and polyethylene components provide that chemical resistance performance necessary for mitigating VOCs, methane, and radon. One of my favorite images from a recent project, just because this is exactly what MonoShield was intended for, due to its enhanced chemical vapor resistance, as well as the installation rates. So we can have our installers, they can achieve anywhere from 40,000 to 60,000 square feet of MonoShield installed per day. So if you're currently involved in designing a soil gas mitigation system for an industrial site, MonoShield would be a great solution to keep really your client's construction schedule, their budget on track, because our installers can really double the installation speed versus a tape applied system. And it offers a true vapor type membrane with its spray applied seams. And lastly, just to kind of piggyback off of Tom related to quality control, this is a major facet for any vapor mitigation system installation. So for all spray applied vapor barriers, there should be many layers of quality control that should be kind of inherently built into the installation process. And that's ultimately to confirm that the system is installed properly. And this starts with the installation being completed by a certified applicator. They are going to conduct thickness verification of the spray applied layer. They're going to perform smoke testing to seal up any pinhole leaks or areas that need to be sealed up that you wouldn't be able to identify from just a typical visual inspection. And then we often recommend a third-party inspector to be out on site to document and oversee the installation and the QA/QC that's happening out on site. That could also include a pre-pour inspection of the membrane to identify any damage or repairs needed prior to concrete placement. So with that, the main takeaways I'd love to leave you all with today are really there's a variety of vapor barrier technologies available for new construction as well as existing buildings. And when you're evaluating different barrier technologies for your site, just keep in mind chemical resistance properties, constructability or ease of application, as well as the QA/QC measures that can be conducted on those particular systems. The modified asphalt and metallized film geomembranes. Those are major advancements that have been brought to the VI mitigation industry. And I think we all know that every site is going to be unique and have its own challenges. It's never one size fits all with designing a vapor mitigation system, but partnering with the right team will truly help ensure successful outcomes for any situation. So please, if you have any questions, let us know. If we aren't able to get to those today, we will get back to you via email or give you a call after this webinar. So thank you guys so much for participating today. And thank you, Tom, for joining us in today's presentation.
All right, thank you very much, Jordan. So that concludes the formal section of our presentation. And now at this point, we'd like to shift into the question and answer portion of the webcast. So we have a question here, and the question is, what are the most common design mistakes that you see, and how could they be corrected?
I think one of the most common mistakes we see is not enough gravel layer. A lot of times we'll see a 3-inch pipe spec and 4 inches of crushed stone. Well, you can't drain the moisture out. You can't get good vacuum distribution. And the other thing that happens is the concrete will crack right along the lines of that 3-inch pipe. So you want to make sure that there's a good gravel layer, at least 2 inches below the pipe and 1.5 inches above. You want to have consistent diameter. You want to embed those probes, and you want to have a direct venting route which goes as vertical as possible. Those are some very basic things that should be integrated into any design.
Okay, thanks, Tom. So here's another question here, and it is, what are the biggest obstacles facing the vapor barrier industry?
I think that the answer to that is kind of broad-based, and it really comes down to education. Educating people who are designing the systems, educating the people who are installing them. Land Science has done a wonderful job through their applicator certification process, but also educating regulators, because different states have different ways of doing things. And if you could Venn diagram the whole thing, you'd have a great solution. And getting everybody on the same page is really critical. That's one of the functions of the Association of Vapor and Intrusion Professionals, is to standardize this so there's a monolith, if you would, of excellence that would get conveyed. And I'm happy to be a part of building that through both AVIP and Land Science.
All right, thank you very much, Tom. So that's going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. For more information about vapor mitigation services from Clean Vapor LLC, you can visit cleanvapor.com. If you'd like to learn more about vapor intrusion barrier technologies from Land Science, please visit landsciencetech.com. Thanks again very much to Tom Hatton and Jordan Knight, and thanks to everyone who could join us. Have a great day.